We're like, no. Damn it.
All right, we're taping now. Come on. Buffer solutions. We're going to do. We're going to find that first a little bit of notes on this, and then I'm going to show you how to do the calculations one way in the first period. That will be the harder way to do them. It'll be the longer way. But I'm going to show you a trick after that in the second period. So some of the homework tonight, 5, 6, 8, and 20, I want you to do this way. And then the rest of the homework, 21A, 23A, and 24A, I want you to do the short way. I'm going to show you. It's like a little trick. But you don't want to show you just the trick. I want to make sure you understand what a buffer solution is. So that's why I'll explain them first. A buffer solution, you got lots of them in your body, all right, in order to maintain the pH. You see, your pH cannot vary by very much at all, or you get very sick and die, all right? You have to have, and there's a lot of ways you're getting acids and bases inside your body besides just drinking orange juice. All right, even just breathing, you're making carbon dioxide in your bloodstream, and that turns into carbonic acid. All right, and there's got to be ways to regulate your pH, or you couldn't survive. Okay, well, buffer solutions are one of the ways you do that. They resist changes in pH. In other words, I can add acid or base to a buffer solution, and it won't change the pH very much. Matter of fact, you'll see that when we do our lab. Probably, we have 2 labs in this chapter. And I think that one will definitely be this week, but I'm not exactly sure which day. We have to talk about titrations. Maybe Wednesday or Thursday this week. This animation doesn't work anymore.
That's a nice one.
I know.
That's very nice. Very clever.
It's one of those dead ones. Like, yeah, that happens.
What happened to animation 1?
That will never work. All right, so acids or buffer solutions can consume added acids or bases without a large change in pH. Okay. Now, what makes up a buffer solution? Well, basically you have to have 2 parts. You got to have a weak acid or a weak base, and you have to have its salt. Okay, it's made up of a weak acid or a weak base, and then the salt of that acid or base. Okay, so the salt, you may remember what a salt is. I'm going to probably don't copy what I'm going to put down here, but I want to show you what a salt basically is. If I add any acid to any base, right? Let's go back. Don't copy this down because I don't want you to think this is the example I want you to use because it's not. I'm going to use a strong acid and a strong base. A strong acid and a strong base, and our most common ones. Our most common ones being hydrochloric and sodium hydroxide. Everybody knows what that gives us from not only from Chem 1, but you can probably figure it out common sense wise. What am I going to get from that? NaCl plus.
H3O.
No.
H2O.
Right, H2O, HOH, right, H2O. So basically, if you add a perfect amount, exact amounts of an acid to an exact amount of a strong base, molarity-wise, you would get a neutral solution, salt and water, just salt water, okay? So a salt is just what you get from reacting an acid to a base. Now, if this is a strong acid, if this were a weak acid and I reacted them with a base, I would get, say for example, we're just going to use HA as my example, where A is some weak acid. It could be F. Hydrofluoric acid is a weak acid, okay? You would get NaF over here, sure enough. And that's what you should look for. It doesn't have to be Na. It could be any of the positive ions in group 1 or even group 2, but usually it's going to be group 1 because we want to keep it monoprotic. So sodium fluoride, could be potassium fluoride, okay? It's going to be the acid reacting with the base is going to give me the salt. So that's the salt of a weak acid, all right? We're going to use HA, so it's probably going to be NaA, something like that, for the salt of it. You get that from reacting. If I add that salt, this is the weird part. If I add that salt, just the salt, to a weak acid, it automatically makes the pH not as acidic. It actually raises the pH, makes it not as acidic, all right? And the same thing's true for a base. Now that seems a little weird, but I'm going to show you why mathematically in a second. And I'm also going to show you why in terms of the equations. So copy that equation down. We use this guy first because he is one of the most famous weak acids we have, and he's also weird looking. It's not one that we're used to seeing. Do you know what acid that is? You should remember him even from organic.
I remember seeing that, but I don't.
Well, let's try drawing him out. If I were to, don't do this, but if I were to draw him out as an organic compound, what would he look like? CH3, COOH, right? Recognize it now? That would be ethanoic acid or acetic acid or vinegar. Okay, it's basically vinegar. All right. Now, I know I mentioned that a couple of times in the past, but I mean, I've never asked you to, there's so many different ways we can see these things, okay? That's not really that important. What's important is the acid acts like an acid. He gives up his H. He's left with this guy behind. That's your A. I mean, most of the time I'm going to be using HA, and that's going to be your A plus hydronium ions, okay? All right. Now, if I also have in this solution some sodium acetate, which would be the salt of that acid, I want you to see what happens and why this works the way it does. First of all, theoretically, like I'm talking about right now. And secondly, in terms of mathematically, what we'll do in a minute.
Is organic going to be on the final? Or is that on
No,
the
that was only in the midterm.
Thank God.
All right, you ready? So here's the crazy part. You have to remember that this guy up here is an equilibrium problem, but this guy is not. All right? So when you add your sodium acetate, which you will do in the we have two labs. The second lab is going to be a qualitative lab. We're going to add sodium acetate directly to a solution of vinegar. And you're going to see what happens to the pH. You're going to see because the indicator is going to change color. All right? And what's going to happen is exactly what you'd expect based on Le Chatelier's principle. I have this guy here first. I add this guy into the solution. This is called the common ion effect. Notice what I've done. When that guy dissolves, what has it done to this concentration of this ion? It's increased it, right? If I got more of this, which way is it forcing that reaction? Back that way. So, and what's it taking with it? Hydronium ions. That's why, without actually adding a strong base to this solution, just adding a salt, the salt of that weak acid, I actually am going to make this guy less acidic because it's going to force him back that way. You see that? That's the point of a buffer solution. All right. Now it's time to see that mathematically. So let's. But before I do, I want to explain what I just said about this is called the common ion effect. I want to show you that with a little bit of notes too, a couple of quick sentences. It's called the common ion effect. Basically, it's a solution that contains the same ion produced from two different sources. And by the way, when we're done with this example I'm going to do in a minute, we're going to look back because we did the same basic example a little while ago without the salt added to it. And sure enough, you can look at the pH from back then, that example, versus this example, and you're going to see a big difference. And it shouldn't surprise us at this point because here's what happens. That ion is going to force it back to the left, basically, and consuming hydronium ions. So that a weak acid with its salt is always less acidic than the same concentration of that acid by himself. Something else, too, you should realize, although I'm not going to investigate that as much until we get to the titrations, when you have both the weak acid and his salt, I can add either an acid or a base, and it tends to be able to resist the change in pH because it will react with one or the other thing, either the salt or the acid, adding an acid or a base. And that's why it's a buffered solution. Okay? All right. So that's the end of the notes. Let's just do one example here. I'm done talking. You should hopefully understand theoretically why, according to Le Chatelier's principle, this works. Now, let's see how mathematically why it works. Okay? Here's my problem. Now notice you're given a Ka. It's a weak acid. No surprise there. You're told the concentration of the acid, and you're told the concentration of the salt. Okay? So let's watch what happens here. I'm going to deal with the salt first because he's the easier equation. He is not an equilibrium equation. We're assuming the salt is a soluble salt. I won't even say that because you should realize that it has to be a soluble salt in order for this to work. So assuming the salt's soluble, what's going to happen? I'll show you. Remember, I have to use abbreviations here. The only acid, weak acid and weak base, I really want you to know the formula for, and don't write these down, are the one I just gave you a minute ago, CH3COOH. Don't copy that down. That's acetic acid. We will use him a couple more times, and he will be on the test. Normally, I'll just use HA for an acid. The only base I want you to know, same thing I did an example with him, would be ammonia, NH3. All right, the only weak base I want you to know. All right, those are, otherwise we're just going to use HA for a weak acid, okay? And so that means the salt of the weak acid, if I use HA, will be NaA, okay? NaA is the salt, all right? That's what he is. He's the salt. This is the salt's reaction. NaA simply breaks up in solution into two things. He breaks up in solution into what two things I'd have to give you?
Na.
Yeah, Na ions, aqueous, and A ions, aqueous. I mean, I don't have to put, you should put the aqueous down there, but whatever.
No, whatever.
Now, if I tell you that you have it tells you right here, it has 0.20 molar of its salt, so 0.200 molar. This goes 100% that way. How much do I have of the sodium ion? 0.20 molar. It all gets converted to that, and 0.20 molar of this. Got it? Makes sense. Now, let's do the equilibrium problem. This is for the acid. This is for the acid. What is he going to look like? He's going to look like any other acid equilibrium expression. It's going to be HA plus H2O yields reversible hydronium ions plus whatever this negative ion is, A negative. And again, these are, I don't normally write AQ in, but I'll just do it this time. Usually shorten up a little bit. Okay. Now, if this were an equilibrium expression, normally, what would I write down? My initial concentration of HA is 0.100 molar. I would ignore water because he's constant. My concentration of the hydronium would be what? 0. And the concentration of this should be 0, but it ain't. It's 0.200 molar from him. That's where that comes from, because he dissolved in there already. Initially, he's already there. That's the crazy part about this guy. Now, the question then becomes, you might be thinking to yourself, well, which way is it going to go? It can only go one way if you think about it, guys. Which way does it have to go? That way. Because I got 0 of this. I can't very well react none of that with that. Okay, it's got to get more of this. You understand? If I've got a 0 on one side, and if you don't believe me, you can solve for Q. Believe me, it'll work out. It has to go that way. So it's minus X, and plus X. And then I got 0.100 minus X, and X. Oh, I'm sorry, my fault. I'm just so used to writing that. Probably like you guys will be too. You're just so used to writing the same thing in that spot. 0.200 plus X. Okay. All right. Now, let's solve the equilibrium expression like we always would. Ka is going to equal products over reactants, hydronium times the A over HA. I don't care about water. I know Ka is 3.50 times 10 to the negative 6. The hydronium is X times X, or 0.200 plus X over 0.100 minus X. Now this may look confusing, but as you already know from a couple of days ago, I can simplify this, can't I? This is a 0.2, by the way. I know it's a little ugly there. All right? I can simplify this. What can I do? I can get rid of the X on the bottom, and guess what? I can get rid of the X on the top, too.
Oh, boy.
And isn't that nice? Why is that nice? Because the problem becomes a lot easier now, right?
Yeah.
right. Well, first of all, before I solve it with the rest of the algebra and math, let's stop doing the calculators. Look up here for a second. Let me explain. The reason we were able to ignore the x when we were subtracting away x is it was so small compared to him. As long as this guy is -4 or bigger, I'm sorry, -4 or smaller, and as long as this number here and here is 0.05 or bigger, you're good. Okay. Now, if I can ignore x because I'm subtracting him away from a large number, guess what? I can ignore him when I'm adding him to a large number, right? So just for the same reason, I don't have to keep either of those x's in here, and the problem basically becomes 0.2 over 0.1 times x. What is that? What is that? I make him bigger. Divide by 0.1. I'll be making him bigger by 1. So it'd be 2x, right? Wouldn't it be 2x? 2x equals 3.50 times 10 to the -6. You see where I got 2x, guys? I ignore those, so it becomes 0.2x over 0.1, which is basically 2x.
Sure.
Wait,
If you don't believe me, divide
wouldn't that
it.
make it times 10 to the -7?
I didn't do anything over here yet.
Oh, okay.
I'm just going this divided by him. That's all I'm doing.
So
I didn't cross.
I did that, okay.
Yeah, I could have. You're right. I could have cross multiplied. It would have given me the same answer because it would have been 0.1. That would have been, and then that way it would have been 0.2x. So it would have given me the same answer. What does x come out to be? Do that quickly. 2x equals 3.50 times 10 to the -6 would be what? 1.75 times 10 to the -6, right? Is -6? Still? It didn't change, right? All right. Now that's nice. That's what x is. Which x is hydronium. So hydronium, there's my first answer, equals 1.75 times 10 to the -6. So what's the pH going to be? Yeah, negative log of that. 1.75 times 10 to the -6. Or you can do that one on your calculator. What do you get for your pH? 5.76? All right. Now, I want you to look back at your examples. And somewhere, the other class at least found it, I'm hoping you guys will too. I thought I purposely wanted to do the same problem twice, only this time adding the salt to it. Look back for another place where I had a 0.10 molar solution of a weak acid, and the Ka was 3.5 to 10 to the -6.
Right here.
Yeah, should be one of the previous examples. And what did you get for the pH for that guy?
10.77.
No, you're looking at the wrong one.
Oh, 3.23.
3.23. So look at this. Just adding the salt made the pH go from 3.23 to 5.76. Nowhere near as acidic. Because remember, the lower the number, the more acidic, right?
Sure.
All right. And so this mathematically shows you why, because we forced it back that way, according to Le Chatelier's principle, and you also know theoretically why. All right. Now your homework, even though Lizzie is here, I'll show it to people anyway, are these 4 problems, and they're also over there. I want you to work on them the rest of this first period. Then I'm going to show you that was a heck of a lot of work to do. I'm going to show you, we're going to derive an equation where, believe it or not, I can solve all of this in one simple equation you could do in less than a minute. Okay? So it'll be nice.
Sure.
It's called the Henderson-Hasselbalch